Okay, pre-calculus, let's take a look at what rational functions are all about. First of all, a rational function, or ratio, means fraction. So this entire chapter, we're going to be dealing with functions that are in fraction form. A rational function, R, standing for rational, is going to have a numerator, p of x, a polynomial in the top, as well as q of x, a polynomial in the denominator. Of course, q of x is not the zero polynomial. It can't be zero in the bottom. Let's take a look at what some of these graphs look like. First of all, does anybody remember what 1 over x is called? It's called, you got it, the reciprocal function. The reciprocal function is 1 over x. Now that we have denominators again, we have to start thinking about domain. The domain for this guy is all reals except you cannot be the number 0. Well, if you can't be 0, then that means this graph is going to have a break. These are not polynomial graphs. They are not smooth and continuous. He has an asymptote there, and he has an asymptote on the x-axis. And then maybe you even remember those special points, 1, 1, and -1, -1. This graph is going to approach the asymptote, get closer, closer, but never touch. Really try to get your graph approaching that asymptote. Don't shoot it up into the sky here. Get down to that x-axis. This branch is going to be in quadrant 3, approaching the asymptotes, but never touching. So that is the basic reciprocal function. We're also going to take a look at graphs like this that are reciprocal of functions, but there's a factor down here squared. So we're just going to write a note right here. The factor is squared. So something different is going to happen. The domain is all reals except you cannot be, well, still 0. So he still has his asymptote on the y-axis, and you still have 1 on the x-axis. But if you plug 1 in, you get +1. And if you plug -1 in and square it, you also get +1. So the difference here is the graph is going to be approaching the y-axis by going up on both sides. So the two branches are coming together right there. So when the factor is squared, the graph will approach the asymptote the same way. And you kind of have to have one point here to get you started. It could be going down, down, going the same way too, but we have to have a point so we know that they're both going up. Okay, so to do this section appropriately, we're going to have to really start looking at the domains. All of the rational functions that we study have denominators. So let's look in these denominators. Domain comes from the denominator, and what you do is you set the denominator equal to 0 to solve for the domain. So for part A, it's going to be all reals except x cannot be, which number? -5. For part B, it might be best to look at that denominator in factored form. X plus 2, x minus 2. Okay, that's going to make things easier. So let's say all reals, comma, except x cannot be plus or -2. Okay, moving right along for part C. The domain here, can that be factored? I don't think so. If you can't factor it, and you can't solve and get an answer, you can't find the restriction. The domain must be all reals, and that's it. All reals. Remember that from chapter 2? What if the denominator is just a constant 3? There's no x's down there, so all reals. There's no problem with that. Let's take a look at part E here, and maybe we should go ahead and factor the numerator. Factoring the numerator is nice. And now that you have the same factor, common factors can cancel, and so we get x plus 1. So x plus 1 is the simplified form of this graph. This is just going to be a line. But wait a minute, we never stated the domain. The domain is going to be all reals except, looking at the original function, x cannot equal 1. Even though you do some work and you cancel it out and you get something more simple, you look at the original and you say do not equal 1. So what happens right here when that cancels out? When it cancels out and it disappears, you can't suddenly start using it, so that means it makes a hole right in the middle of the graph. All right, that's cool. Part F, I see no denominator. That's just a linear line. His domain is going to be all reals. Well, F kind of looks like question E. So what is the difference then between problems E and F? Because they both look like lines, but E didn't start off as a line, did he? E has a hole in the graph. So when you look at it, it's going to be an uphill line. The y-intercept is +1, uphill line. But then right here at 1, there's going to be a hole in the graph, and then it keeps going. It's a line with a hole in the graph. Part F, he won't have any holes. A hole appears in a graph when factors do what? Cancel. When factors cancel. And how do you get the y value? You plug x into the new equation. Make sure you write new equation. Okay, so I know that this hole right here is going to be at the point 1, but then how do we find the y value? Let's plug 1 into this new equation. 1 plus 1 gives you a 2. If you tried plugging into the old one, you'd have a problem. Okay, so tonight you're going to practice some domain, and you're also going to practice some graphs. Here we go. We are going to look at some pictures. We're going to state domain and range, and we're also going to state some asymptotes. So let's look at the domain of this graph. Does he have x values everywhere? I don't think so. The first thing I notice is there is an asymptote right here. Use a ruler. Make sure the top and the bottom approach the same way. There is no graph at 2. There's no graph right there. Let's also take a look at the horizontal one. I do not think there's any graph here at this y value. I do have to say that the software I used to make this drew rather fat graphs, so that is approaching but not necessarily touching. It's just really fat so that you can see it. So the domain, all reals except, let's look at the x's. There's no graph. X cannot equal 2. Now let's talk y values. There's no graph, all reals except y. Y cannot equal the number 1. Okay? Horizontal asymptotes, those are the lines going horizontally. That would be a hoi. Horizontals or hois. So we've got y equals 1. There is a vertical asymptote right here at x equals 2. Does he have any oblique asymptotes? I guess it would be nice to tell you. An oblique asymptote means a diagonal line. A diagonal line. Does he have any diagonal lines? No. So we're going to say none, or you can put a dash. The diagonal line answer would be in the form of y equals mx plus b, but he doesn't have any. All right, let's go take a look at this next graph here. This graph, has one of those things where the branches are going up, so it must have had a factor squared. I like to use a ruler so I can make sure I get right in here in the middle. There's a vertical asymptote there, and there is a horizontal asymptote right here along the x-axis. Okay, so the domain, all reals except x cannot equal what number? Yeah, -3. The range. Well, I don't even see any graph at all down here. The graph is all completely up there. The question is, does the graph touch 0? And the answer is no, it does not touch 0. That is an asymptote. So y has to be greater than 0. Horizontal asymptote, that's going to be ahoy, y equals to 0. Vertical asymptote, where is it at? X equals -3. Do you see any obliques? Nope. No oblique asymptotes for that guy. Okay, this next one's going to get a little more interesting. I do see some diagonal action happening. So the first thing I'm going to do is make sure I get these asymptotes drawn in nicely. The first one, I notice that there's a split in the graph right here along the y-axis. This one's going up, this one's approaching down. So there's an asymptote. Now what about this side of the graph? This one looks to be approaching a diagonal line. Let's get it nice and lined up for both sides. That is a diagonal or an oblique asymptote. Oblique. Okay, domain. All reals except x cannot equal 0. The range for this one. The range. If I look at this branch, it's going down all the way. And this branch is going up all the way. The range for this graph is all reals. Intercepts. Anywhere you cross any of the axes. Does this graph touch the y-axis? No, it cannot. That is an asymptote. Approach but never touch. Does it cross the x-axis? Oh yeah, in these two places there. I see two x-intercepts. I'm going to write them as points. Plus minus 1, 0. Horizontal asymptotes. This graph did not have any. So you can write the word none or put a dash. Don't leave it blank because that looks like you forgot to answer it and it might take points off. The vertical asymptote is x equals 0. And the oblique asymptote, remember, we have to write a diagonal line. So y equals, let's go figure out the slope of this line. Up 1 over 1, up 1 over 1. It's going all the way through 10, 10. It looks like the slope is 1, 1x, and the y-intercept is 0. So that one was nice and easy. Okay, let's do a couple of more. We're going to look at graphs that might have 3 pieces to them, and it's going to work exactly the same. So the first thing I'm going to do is look at the graph, take out my ruler, and see if I could find clearly where this graph splits. The top branch and the bottom branch must both approach the same asymptote. And I think this one might be right here along this value, so let's go ahead and mark that in. And then the horizontal one's going to be going right here like that. Okay, I think I have them all drawn. That is going to help me write my answers down. Is there any horizontals? At y equals 0. Verticals, there's 2 of them. So I'm going to say x equals plus and minus 2. You don't have to write it together. You can write 2 separates. Are there any oblique? No. Okay, let's just put a little note here. Okay, answer with either the words none or dash. But don't leave it blank. Make sure you answer the question. Okay, this last one here is really nice and big. Make sure that you use a ruler so you can find the asymptotes. Let's see, it's got to be the same for the top and the bottom. This one definitely crossed this value. So I have to go to the next x value. Is that going to be the same down there? This graph, this branch definitely crossed -1, 2, 3. So it must be approaching -4. Probably gets closer as you go further down. So I think I found that vertical one at 1, 2, 3, -4. Okay, understand what I'm talking about here? It has to be the same vertical line for top and bottom. If it looked like it crossed it already, go to the next number. This one's approaching really fat, but it is definitely 3. The horizontal one here, let's see, it's not 1, and it's not 2. What about 3? This one looks like it's approaching 3, but this one looks like it crossed 3. And then we have an interesting discussion up here. The horizontal asymptote got crossed right here, but that is okay. What? I thought you weren't supposed to touch. Well, the horizontal asymptote is not there for the middle. The horizontal asymptote is there to guide the ends as they go further and further out. He does not have the same restrictions in the middle. You can cross in the middle. Oh, that's so funny. Horizontal asymptote, y equals 3. The vertical asymptotes are x equals 3 and x equals -4. There's no oblique asymptote for this one. So we have to make sure that we write a little note down here because something interesting happened. Okay, what do you notice about the graph and its horizontal asymptote right there? The graph is allowed to cross the horizontal asymptote. Okay, he is allowed to cross the horizontal asymptote. The reason that that asymptote is there is for the ends. It helps the ends go horizontally. It does not dictate what happens in the middle. It helps the ends go horizontally, so you can cross it as long as you start approaching it there at the end. Okay? Can you, after watching this video, state the domain of a rational equation? I hope you know that you have to look in the denominator. Can you graph a reciprocal function using transformations? We didn't really talk about that yet, so we'll do that tomorrow. Can you state the horizontal, vertical, and oblique asymptotes by looking at a graph? Have a great day, everyone. I'll see you tomorrow.